All right, let's dive in. Today, we're going to talk about the fundamental rules that run, well, pretty much everything, from the air we breathe to the food we eat. We're going to get into the simple logic behind some of chemistry's biggest and kind of weirdest puzzles.
So let's kick things off with a little thought experiment. On one side, you've got sodium. This is a metal that is so incredibly reactive, so unstable, that if you drop it in water, it literally explodes. On the other side, you've got chlorine, a gas so toxic, it's actually been used as a chemical weapon. Nasty stuff.
Okay, so you take these two, let's be honest, dangerous elements, and you combine them. What do you think happens? You'd probably guess it's a catastrophe, right? But what you actually get is something you probably eat every single day. Plain old table salt. So how on earth is that possible?
To figure out this bit of chemical magic, we need to zoom way, way out. We have to start with the most basic question of all. What is everything in our universe actually made of? Well, the answer is atoms. They are the tiny, fundamental building blocks for all matter. You can kind of picture them as these tiny little solar systems, right? You've got a core in the middle, like the sun, made of protons and neutrons, and then you have these electrons just whizzing around it in orbits. Now, the real key to understanding basically all of chemistry comes down to a special group of these electrons, the ones on the very edge, in the outermost shell. They're called valence electrons. And here's the secret. Almost everything that happens in chemistry, from explosions to life itself, is really just the story of what these specific electrons are doing.
Okay, so there are over 100 different kinds of atoms out there. How in the world do scientists keep track of them all and, more importantly, predict what they're going to do? Well, they use what I like to call the ultimate chemistry cheat sheet.
I'm talking about the periodic table. And you got to understand, this isn't just some random chart of elements they make you memorize in school. No, it's a brilliantly organized map. If you know where an element is on this map, you can figure out how it's going to act. It's predictive, it's powerful, it's kind of genius.
And the logic behind it is actually super elegant. See the columns? Everything in the same column tends to act in a really similar way. Think of them like family members. And why? It's because they all have the exact same number of those all-important valence electrons. It's a family resemblance, but at the atomic level.
So we know how atoms are organized, but that just brings up the next big question, right? Why do they even bother interacting in the first place? What's driving them to connect with each other and form molecules? I mean, what's their motivation?
It all comes down to one of the most basic rules of the entire universe. Everything, and I mean everything, from a boulder on a cliff to the smallest atom, wants to be stable. It wants to find the lowest, most relaxed energy state it possibly can. It wants to chill out.
So what does chilling out mean for an atom? What's its ultimate happy place? It's having a completely full outer shell of electrons. That's the goal. For most atoms, that magic number is 8 valence electrons. That's the state of maximum stability.
And atoms will do pretty much anything to get that full shell. They will share electrons with a neighbor, they'll give one away, or they'll just straight up steal one from another atom. And that whole drama, the begging, borrowing, and stealing of electrons, that's what we call a chemical bond.
And they basically have three main strategies to do this. First up, the ionic bond. This is a simple transfer. One atom gives, the other takes. That's what holds salt crystals together. Then you have the covalent bond. This is all about sharing electrons, like a partnership. That's the backbone of things like water and even plastics. And finally, you've got the metallic bond, where electrons are, as chemists say, promiscuous. They just move around freely in a big cloud, which is what makes metals so strong and able to conduct electricity.
All right, so let's circle all the way back to our original mystery. Now that we know about valence electrons and this universal drive for stability, how does an explosive metal and a toxic gas combine to make completely harmless table salt?
Well, it's really a perfect chemical matchmaking story. Sodium has one lonely valence electron it is desperate to get rid of. Chlorine, on the other hand, has 7 and needs just one more to feel complete. It's a perfect match. So sodium just hands its electron over to chlorine, bam. Now here's the catch. Since they've lost or gained a negative electron, they're not neutral anymore. They've become charged ions. Sodium is now positive, chlorine is negative. And what do opposites do? They attract. They stick together like tiny, powerful magnets, forming that stable crystal of salt. And this is the most crucial part. The new thing they create, salt, has completely different properties from its ingredients. That dangerous, reactive personality of sodium and chlorine, it just vanishes. Why? Because both atoms have finally achieved what they wanted all along, that stable, low-energy state. They are content.
So this whole process of making and breaking bonds to create new, more stable stuff, we call that a chemical reaction. But do they just happen on their own?
Not exactly. I mean, think about a log for a campfire. It's surrounded by oxygen, but it doesn't just spontaneously burst into flame, right? You need to give it a little push to get it going. You need to strike a match. That little bit of starting energy is called activation energy.
Now, some reactions are like a ball sitting at the very top of a hill. Once you give it that tiny nudge of activation energy, it just takes off, rolling all the way down by itself and releasing a bunch of energy along the way. We call those exothermic reactions. Think exo for energy exiting.
But then you have the other kind of reaction. These are like trying to push that same ball uphill. You have to keep putting energy in constantly. The moment you stop pushing, the reaction stops. These are called endothermic reactions because they absorb energy to keep going.
So when you boil it all down, that's really what's going on. From the most violent explosion you can imagine to the silent process of rust forming on metal, all of chemistry is just this grand, beautiful story of electrons moving around, always trying to find the most stable, most low-energy arrangement they possibly can.
Which kind of leaves us with one final thought. These exact same simple rules are driving countless tiny reactions in the air you're breathing and even inside your own body right this very second. So, what other invisible chemical dramas are unfolding all around you right now? Thanks for joining us for this explainer.